So you started. Okay. So good morning, friends. Yeah, yes. So good morning, student friends. Another day. So once again, welcome to all for this session, and also thank my own friends for making all these arrangements and making it possible. So, and yesterday we have discussed at length about analysis of fluid flow. So in that case, we have discussed almost all the problems except very few. So because the importance, I have not gone in a hurry way. So that's why I took it today. And also we will complete the other chapter, orifice and notches chapter, a small chapter of, but generally we are getting the questions in that chapter also. And the problems on that, and we have some objective questions also. I have taken up 40 questions. We'll try to complete that, and tomorrow, the last class, I will be taking another important chapter, last chapter in fluid mechanics, that is drag, lift and drag, and also boundary layer. And so I have given almost all equations, all relevant information. Definitely you are going to get good marks in this particular subject when you write gate examination. So it is all over, and we are. I have done problems in this chapter. So we have, if I remember, 16 questions. So we have 4 questions left over. I will complete those questions. Yes, yes. So I completed this problem. So water flows through a 100 m diameter pipe with a velocity of 0.015 meters per second. If the kinematic viscosity of water is 1.13 to 10 power minus 6 meters square per second, the friction factor of the pipe material. So this we have discussed yesterday. A very simple problem here. He has given kinematic viscosity and diameter of the pipe is known here, velocity is known here. You can find out Reynolds number. Reynolds number is Vt by nu. V is the velocity, 0.0 divided by 1.13 into 10 power minus 6. So that is Reynolds number is 1327.433. When the Reynolds number is less than 2000, we have a relation between the quotient of friction and Reynolds number. So F is equal to 64 by Rn. The relation between F and Rn. He has asked to find out Darcy friction factor 64 by Rn. So 64 by 1327, it is 0.0482. So that is the answer. We have discussed that. And this is the another problem. A 2 kilometers long pipe of 0.2 meters, 2 reservoirs. Difference between water levels in the reservoir is 8. Darcy's Swisbass friction factor of the pipe is 0.04. Accounting for frictional entry and exit losses, the velocity in the pipe is. So we have answers here, 0.63, 0.35 need to, length of the pipe is 2 meters. In other words, you can take 2000 meters. Length of the pipe means it is between reservoir A to B or 1 to 2, whatever it is, and water level difference between two reservoirs. So this is one surface here, this is another surface here, the capital H, water level surface between two reservoirs. So you can straight away take the water level surface between two reservoirs is equal to sum of losses straight away, or you can write Bernoulli's equation also. I will let you know the procedure. And the length of the pipe is 2000 meters and diameter of the pipe is 0.2 meters. Diameter of the pipe is 0.2 meters and head of water, this is head here, head of the water is 8 meters and friction factor is 0.04. And we have losses here. I told you it is required for you to remember each and every equations. As you know, the entry loss here is 0.5 V square by 2Z and exit is V square by 2Z. And the velocity of water in pipe is not known. So velocity of water in pipe is not known. So we have total losses here. Friction loss FL V square by 2ZD. So F is 0.04 he has given and L is 2 kilometers. You need to convert it to 2000 meters. V velocity is not known and G is 9.81 meters per second square. And D is, so FL V square by 2ZD, it is known here. It is known here. And 0.5 V square by 2Z, this is the 0.5. 0.5 V square by 2Z, this is V here. And V is the velocity. Is not known here. 0.5 V square by 2 into 9.81 plus V square by 2Z, 2 into 9.81. So the equation will be getting, so this is every notation, I mean every step is in terms of V square. So the final one is 20.465 V square. So actually straight away you can take, so these are the sum of the losses which is equal to water level difference between two reservoirs. So you can straight away equate these losses to 8 and find out the velocity. But the step here is how you got that the water level difference between two reservoirs is equal to sum of losses. So that is the simple equation here. Apply Bernoulli's equation between 1 and 2. Top surface here. So this is the pressure head, velocity head and datum head. Pressure head, velocity head and datum head plus losses here. So here, if you see here, this is the pressure at point 1, pressure at point 2. Pressure at point 1 and pressure at point 2. The pressures are atmosphere, and you can neglect the pressure, atmosphere pressure for pressure measuring instruments. So you can take P1 is equal to 0 and P2 is equal to 0. And regarding the velocities here, V1 and V2, so the velocity, suppose if you consider the velocity somewhere here, so the velocities V1 and V2 are equal to 0. So you have the same velocity and you can take, this is also equal to 0. This is the static tank, static head here. When the head is static, whatever the slight changes here, whatever the flow here will not have any effect in the velocity of the water. So the velocities are normally at point 1 and 2 are equal to 0. So Z1 is 8 meters here for this and Z2 is 0 here. So Z1 is 8 meters here, Z2 is 0. In other words, all are 0. So the losses is equal to the capital H. So that is Z1. So Z meters which is equal to losses here. Straight away you can take the sum of the losses, take friction loss and entrance loss, exit loss, and you can make equal to H which is also same. So straight away this is equal to 20.465 V square. It is equal to 8 and you can find out the velocity which is equation here. Not a difficult problem, just find out the losses and made it equal to the water level difference between two reservoirs. The other important problem, an incompressible fluid is flowing, pipe divides into two horizontal parallel pipes of diameters D1 and D2. He has also given D1 equal 4 times D2. Again join back to a pipe. So this is the problem under when the pipes are connected in parallel. So join back to a pipe of the original size. For both the parallel pipes, both the pipes are parallel and connected to main pipe. Again, the head loss due to friction only, and the dot viscous friction factor is to be same. F is also has given same. The velocity ratio between the bigger and the smaller branched pipe. He has asked to find out the velocity is d2 and d1 is equal to 4 times d2. One is a bigger pipe and another one smaller pipe. And distance L apart, and then again join back all these things here. So here this is a simple problem under the flow through pipes when the pipes are connected in parallel. So this is d1 is equal to 4 times he has given. So one pipe having two diameters here. So one d1 is equal to 4 times d2 and d2 is also given. So d2 is the diameter here and d1 is the diameter which is equal to 4 times d2. First v2 here. So the quantity of water which is flowing here, what is the flow through pipes when the pipes are connected in parallel? So the main pipe divided into two parallel pipes and again joined together and formed as the main pipe. So this Q is equal to Q1 plus Q2. So this Q is equal to Q1 plus Q2. That is one equation here. So for parallel pipes, other equation, there are two equations for pipes connected in parallel. One equation is Q is equal to Q1 plus Q2. That is one equation. And second equation is the losses here for the pipe 1 is equal to losses here for the pipe 2. So for the pipe 1, what are the losses, and for the pipe 2, what are the losses? For parallel pipes, the head loss is same. So HF1 is equal to HF2. And friction factor also given, that is same. So you can straight away take the equation HF1 is equal to HF2, F1 and F2 are equal. So you can cancel F1 F2 and L1 and L2 are same. You can cancel L1 and L2 and you can also cancel 2Z and 2Z. Here is we'll be getting, so this is D1 square by D1. So this is D1, not D2 here. So V1 square by D1 and which is also equal to V2 square by D2. So here, so we have given here, so V1 by V2. So V1 by V2 is equal to V2 by V1. So here, the diameter here, so D2 here, the diameter here, D2 by D1 here. So V1 by V2 means it is D1 here. We will be going this side. So V1 by V2 is equal to D1 by D2 here. I mean V1 square by V2 square is equal to, here this is D1. So typing mistake here, D1 by D2. So D1 is 4D2 by D2. This is 4 here. So V1 by V2 is equal to 2. So the ratio between the velocities in the pipe 1 and pipe 2 is 2 here. Another problem, interesting problem given in gate examination. A pipe of 0.7 meters diameter has a length of 6 kilometers. A pipe of 0.7 meters diameter has a length of 6 kilometers and connects two reservoirs A and B. The water level in reservoir A is at an elevation 30 meters above the water level in the reservoir B. He has given head. Pipe 0.7 meters diameter, length 6 kilometers, two reservoirs, and water level is 30. Halfway along the pipeline, there is a branch also, branching system, branch through which water can be supplied to a third reservoir. The friction factor of the pipe is 0.024. The quantity of water discharged into reservoir C is 0.15. Considering the acceleration due to gravity as 9.81 meters per second square and neglecting minor losses, the discharge in meter cube per second into the reservoir B is. So we have the continued equation here, and here we have a tank A here, and this is tank B. So the water is traveling from tank A to tank B, and there is a junction here, and the water is also flowing into this direction. This is also C. And he has given the diameter is 0.7 here, this is diameter is 0.7, exactly at halfway. Total length of the pipe is 6 kilometers, but exactly at halfway, after 3 kilometers, there is a branch here. And this is 3 kilometers and this is 3 kilometers here, and head water level difference between two reservoirs is 30. and QA is the quantity of water which is flowing through this pipe here, and QB the water which is flowing through the pipe here, and QC is the water flowing through the pipe here. And the quotient of friction factor F is 0.024 for all the cases. We don't have the values of Q1, Q2, but he has given QC. So QC is equal to 0.15 meter cube per second, and he has also given the diameter. Diameter of the pipe is same for all the pipes here. So then use continuity equation here. The water which is flowing from here to here, QA, which is equal to some of the water going this direction, some of the water going this direction. So QA is equal to QB plus QC. The first equation here in branching pipes. So QA is equal to QB plus QC. So QA is equal to QB plus QC, and he has given the value of QC. QC is 0.15 meter cube per second. So we have the value QC here, and this is one equation, let's say. So for the reservoir A to reservoir B, find out the loss of head A to B. So take A to B and find out the loss of head. So for the flow from reservoir A to reservoir, the loss of head is, you can take FLV square 2GD or FL QA square. So because the QA and QB are not known, so it is required to find out QB, the quantity of water which is flowing through the pipe B, and you can convert VA into QA by VA. Q is equal to AB, so V is equal to Q by A. So that you can convert, and so the equation for loss of head FLV square 2G, the same equation, but he has converted V in terms of Q and B. That's why it is G.V.R here. So FA LA, this is also LA, not B here. FA LA QA square by 12.1 into dA to the power of 5 plus the loss of friction up to here. This is A pipe. So L1, so FA is 0.024, L1 is 3000, and the discharge QA is equal to have the value QB plus 0.15. So this QA is known here, QB plus 0.15 and 12.1, and diameter A is 0.7 here to the power of 5. This is to the power of 5 again, plus for the other pipe friction loss, so 0.024 into 3000 into QB square. So the discharge at point B square by 2G 12.1 into 0.7 to the power of 5. So the complete equation, this is equal to the loss of head is equal to the losses is equal to the capital H, reservoir water level difference between two reservoirs H is equal to losses here. So H, this is equal to 30. So simplify this equation, this is all in terms of QB, and we have the value here, so we can find out QB, which is 0.572 meter cube per second. So this is the 5 marks question given in the examination, the last problem in in this chapter. Two pipes A and B, see here, two pipes A and B are connected in parallel between 2 points M and N as shown in the figure. Pipe A is of 80 mm diameter and length 900 meters. Pipe B is of 100 mm diameter and 700 meters long. And its friction is 0.018 and its friction is 0.018. Calculate the discharge in the two pipes. So here, so we can, so there are two pipes here. One is having 80 mm diameter, other one is having 100 mm diameter, 80 mm diameter, 100 mm diameter. And the length of the pipe 1 is 900 meters, length of the pipe 2 is 700 meters, and the friction is different values here. FA is equal to 0.015 and FB is equal to 0.018. And he has asked to find out. So this is again the pipes are connected in parallel. We have two equations for pipes connected in parallel. Here the discharge which is flowing through the main pipe, which is equal to sum of the discharge through the parallel pipes, Q is equal to Q1 plus Q2. And the losses here in A, which is equal to losses here in B. That is the only equation. Based on that, we can find out discharge in the two pipes. So total discharge has given 0.030 meter cube per second. Let QA and QB be the discharges in pipe A and B respectively. So QA is the quantity of water which is flowing through the pipe A here, QA, and A is the cross section area, and FA is the friction factor here, FA is the friction factor 0.015, and ATM diameter 900 meters length, and this is 100 mm diameter and 700 meters length, and friction factor B is 0.018. So length of the pipe here, diameter of the pipe, friction factor for the pipe, length of the pipe for B, and all these things, length, diameter, and friction factor here. So the equation here is the quantity of water which is flowing through the main pipe is equal to quantity of water which is flowing through the pipe A and pipe B. So head loss across pipe A also equal to head loss across pipe B. So that means the friction losses for pipe A is equal to friction loss for the pipe B. So then use the equation here, friction losses for pipe A, that is FLB square by 2GD, and you can also take which is equal to 8F LQA square by pi J D phi A. So because this you can convert V square into Q by, V is equal to Q by A, substitute V by Q by A. So the equation is here 8FA LA QA square by pi square G D phi A. So which is equal to 8FB LB QB square by pi square G D phi B. So everything is known here except QA and QB, and F value is known here. So you can rather cancel 8 by pi square G on both sides. You can straight away take FA. So FA is equal to 0.015, and the length is 900 meters, and QA is not known, and diameter is 0.08. ATM diameter means you can convert into meters here. And similarly FB, 8 by pi square G, you can cancel FB is equal to 0.018, and length is 700 here, and QB is not known, and the diameter is 100 mm, converted to meters 0.1. So you can get the relation between QA and QB here. QA is equal to 0.55 QB. So then QA plus QB is equal to 0.03, which is equal to 0.55 QB plus QB, which is equal to 0.03. So you can find out QB here, 0.03 by 0.55, which is equal to 0.02 meter cube per second, and QO, once you have the value, so because we have the value of Q here, so the value of Q has given, so you can find out QA also, so the 0.5 QBB, and we have the relation here QB and QA is QB, so you got QB here, you can also find out QA, that is equal to 0.01, so here QB, so 0.01 plus 0.02, 0.03 meter cube per second, which is flowing through the main pipe. So this is also important problem, nothing the complicated here, very easy problem. So you can also solve such type of problems, even bigger problems of 5 marks question, provided you have a provided you are strong in making equations and understanding of entire theoretical background. So with this, this chapter is completed. So you can go to the next chapter. This is another chapter, important chapter. Easiest chapter of all the chapters. Orifices and notches. Orifices and notches. So the orifice is a small opening. Orifice is a small opening provided in the side of the tank. For example, see here, this is called orifice. So this is here, this is called orifice. This is called orifice. So orifice is an opening here, is the opening here providing the side of the tank through which fluid is flowing. What is the purpose of this orifice? You can find out the quantity of water which is flowing through a tank. So the purpose of the orifice is again to find out the rate of flow. The purpose of instrument and orifice meter for finding out the discharge flowing through a pipe, and petard tube is required to find out, it is for finding out the velocity, whereas this orifice and mouthpiece, we have mouthpiece also, orifice and mouthpiece, so those are for finding out the discharge which is in the tank. So this is the orifice here, opening providing the side of the tank through which fluid is flowing. And mouthpiece means we have a small length of the tube connected here, the length of the pipe here is 2 to 3 times the diameter of the pipe. The length of the pipe is 2 to 3 times the diameter of the pipe, and which is connected to this point, and the water is flowing, and now with it smoothly, and the flow is regulated with the help of a small pipe here. So then what is the difference between orifice and mouthpiece? For example, you take orifice here, and the water is coming out directly into the atmosphere. We have more losses here in the orifice, whereas in the mouthpiece, a small length of the pipe is connected. Length of the pipe is 2 to 3 times the diameter, connected here, and the water is flowing through the pipe and coming out into the atmosphere. The losses are minimized with the help of a small pipeline which is connected. That is called mouthpiece. So in other words, mouthpiece the losses are less, and orifice the losses are more. Then for which case the coefficient of discharge is more? Important question. So when the losses are more, as you know, the coefficient of discharge is equal to Q actual by Q theoretical. Theoretically, the water which is supplied, and actual means the water which is actually available. So as the losses are more, the actual discharge is always less than theoretical discharge, much less than theoretical discharge if losses are more. So the CD value is less for orifice, around 0.6 to 0.7 compared to mouthpiece. So the coefficient of discharge for the mouthpiece is 0.85, 0.855. It is 0.85, around 0.85 value coefficient of discharge for the mouthpiece. Clear cut difference here between orifice and mouth. The procedure, entire procedure, everything is same for finding out discharge, etc. Then what are the different, small and large orifice? So small orifice is when head is more than 5 times diameter. When head is more than 5 times diameter, we can say that it is a small orifice. When head is less than 5 times diameter, we can say that it is a large orifice. For example, H is head above. So suppose if you see the line here, this is the line which has drawn to the center of the orifice. So this is the orifice here, diameter is here, and this is drawn through the center here. So this is H here. So when H is more than 5 times the diameter, we can say it is a small orifice. When H is less than, when head above center of orifice up to the water level surface. So when it is less than 5 times the diameter, when H is less than 5 times the diameter, we can say it is large orifice, small orifice and large orifice. And it depends on the cross section. For example, this is rectangular orifice. We can have a triangular orifice. This is okay. So this is rectangular orifice here. This is triangular. Okay, we come to that. Okay. So we have a rectangular orifice and triangular orifice, a square and circular orifice. It depends on the cross section. We have a rectangular orifice, triangular, square, and circular. And also it depends on the discharging. We have free discharging, partial, and fully submerged orifice. Free discharging orifice. So this is free discharging orifice. So when the water is coming out freely without any flow here, so the water is coming out in the atmosphere, then it is called free discharging orifice. For example, see here, yes. So here when the water is coming into the other tank, so it is not, it is not coming into the atmosphere, so this is also submerged here. So now it is a fully submerged orifice. This orifice is completely in water. So this is tank 1 and this is tank 2. So this is completely submerged in water. So this is a fully submerged orifice. And suppose if you see here, this is a partially submerged orifice. Partial submerged orifice means only part of the orifice, half of the orifice is submerged and half is open to the atmosphere. So this flow is coming out into the atmosphere, whereas this flow is coming into the water. So this is a partially submerged orifice. Partially submerged orifice means partially submerged and partially open to the atmosphere. So these three are the different types here. So then how will you find out the coefficient of discharge? As you know, coefficient of discharge is actual discharge by theoretical discharge. Actual discharge by theoretical discharge. So as you know, the square, the actual discharge, this is the theoretical discharge here, flow through a small orifice, So I can apply, we can apply Bernoulli's equations here. Okay, or side we can take, so as you know, the orifice here, flow through small orifice, so straight away we can take that CD, so the actual discharge by theoretical discharge is quotient of discharge. So the quotient of discharge is equal to Q actual Q theoretical. Theoretical is A into velocity. A is the cross-section area of the orifice and the velocity is square root 2gh. What is the h here? So this h is the head above center of orifice. So Q actual for the small orifice, that means when the head is more than 5 times the diameter of the orifice, which is equal to quotient of discharge CD, and area of the cross section of the orifice pi square by 4 and the square root 2gh, and g is gravity and h is the head above center of orifice. Then we have a relation which is the quotient of discharge is equal to quotient of velocity into quotient of contraction. Very, very important equation here, and we have a gate problem also in this equation, So CD is equal to CB into CC. For example, you see here what is quotient of discharge, as you know. What is the quotient of CC, quotient of contraction? What exactly mean by quotient of contraction? So quotient of contraction means, I'll come to that. As the water is coming out, what happens here? The jet goes on reducing and again increasing. So the point up to which when the jet has minimum cross-section area is called Wiener contract. We have discussed this in other chapter in application of Bernoulli's equation. So Wiener contract is the place, this is the point here, at which the jet has minimum cross-section area. So the distance from side of the orifice to the Wiener contractor is d by 2. It is d by 2. And if the diameter is d here, it is d by 2 if the diameter is d here. So here this is Wiener contractor here. Then quotient of contraction is equal to the area. So the area of the jet here, at Wiener contractor by the area of the jet. Come on. 1 minute and I will be back. So this is quotient of contraction. So quotient of contraction CC is the area at Wiener contractor by the area of the orifice. So the quotient of contraction is the ratio of areas. So the area of jet has the jet has minimum cross-section area at Wiener contractor. So the area here at Wiener contractor by the area here. So that is quotient of contraction around 0.6 to 0.7 the value. And similarly quotient of velocity. So the velocity of the water here, V actual by V theoretical, quotient of velocity and quotient of discharge. So based on that, CD is equal to CC into CB, important equation. CD is equal to CC into CB. Then how will you find out? So we have discussed about small orifice. So CD is equal to CB into CC. Now flow through large rectangular orifice. Then how will you find out? When there is a flow through large rectangular orifice. So this is a rectangular orifice here. So this is a rectangular orifice here. The head here is, this is the top surface. So this is the cross section here. So this is the cross section here. The head here is H1 up to the top edge. So this is R5. This is R5, rectangle R5 here, and H1 is with reference to top edge, and H2 is with reference to bottom edge, and H is exactly with reference to center. The capital H with reference to center. Then how we are going to find out the flow through large rectangle R5s? Large rectangle R5s. How will you find out the discharge? So take small strip. Similar to this, take small strip here, small strip. The thickness is DH and the width is B here. So what is the area of small strip? The area of the small strip is B into DH. What is the velocity of the water which is flowing the small strip? Which is square root 2GH, where H is the, its location with reference to free liquid surface. So the actual theoretical discharge, which is flowing through a small strip of thickness DH, like is equal to B into DH and square root 2GH. B into DH and square root 2GH is the discharge which is flowing through this theoretical discharge multiplied by quotient of discharge, that gives the actual discharge. So the equation is actual discharge which is flowing through this small strip is equal to quotient of discharge multiplied by the area is B into DH multiplied by square root 2GH. Yes. So dq strip which is equal to quotient of discharge multiplied by B into DH and square root of 2GH, where H is this capital H is, don't confuse H2 and H1. So this capital H is head above center of R5s. Then how will you find out for the entire R5s? Only do integration here, integral dq actual and integral square root 2GH into DH. So CdB is constant and integral 2g square root 2gh into dh. You can also take out this 2z. So CdB root 2z you can take out and the integral h power 1 by 2 into dh. So now the limits are, if you see the limits here, so the limits are h2 to h1. So we have one, so the maximum value of h can be, either it can be h1 or it can be h2. So limits are h1 to h2. So if you do integration, then the equation is the Q actual is equal to 2 by 3 CD is the quotient of discharge, B square root 2Z into h to the power of 3 by 2 minus h1 to the power of 3 by 2. This is the important equation. You can as well remember or you can derive, up to you. But the equation you should be remembered perfectly. 2/3 CD is the quotient of discharge. Now 0.6 to 0.7 and B is the width of R5. And square root 2z. What is H2 here? H2 is the location of bottom edge of the R5s. H1 is the location of the top edge with reference to the R5, top edge of the R5s. What level difference? So if you take H1 and H2, it should be clear. So H1 is with reference to top edge and H2 with reference to bottom edge and H with reference to the center line. You should remember all these things. Now flow through fully submerged R5s. So this is the fully submerged R5s now. Then how we are going to find out for fully submerged R5s? Same equation, same procedure. Once again, try to remember this H1 is with reference to top edge and this H2 is with reference to bottom edge. Whereas this H not with reference to center line. So this H is the water level difference between two reservoirs here. This is the reservoir A and reservoir B, or tank A and tank B, in which water is flowing from one tank to other tank. And as the R5 is completely submerged, so it is called submerged R5s and fully submerged R5. So this is fully submerged R5s here, and this capital H is not with reference to center of the R5. So this is with reference to the water level difference between two reservoirs. So the equation is Q actual is equal to CD is the quotient of discharge. CD is the quotient of discharge. What is this H here? So this H for the fully submerged R5, this is between the water level surface between two reservoirs. So now fully submerged R5, we have the equation, and large rectangular R5, free discharge, we have the equation here. Then how will you find out for flow through partially submerged R5s? The equation more or less same for R5 and mouthpiece. Only quotient of discharge is 0.6 to 0.7 for R5 and the mouthpiece is 0.8 to 0.85. So for partial submerged R5, we see here, this is partial submerged here, open to atmosphere. So this is a partially submerged R5s. So up to half it is completely submerged and above half is completely open. Then how will you find out for the discharge through partially submerged R5s? So here, this you can take it in two parts here. So one part is, let us say the discharge through partial submerged R5s is here Q1 and here Q2. The water which is flowing through the above center of the R5s is, let us say, Q1 and below center of R5s is Q2. What is Q1 here? Q1 is the quantity of water which is flowing through the rectangle R5s into a free discharging, and Q2 is the quantity of water which is flowing through the R5s under fully submerged condition. So the partially submerged R5s you can take, it is free discharging plus fully submerged condition. Top free discharging R5s and bottom fully submerged R5s. So take only top half here. Take only top half here. So now the top edge is H1 and the bottom is only H here. So take the equation. So one free discharging, we have equation here 2/3. C is the quotient of discharge and B is width of the R5s and square root 2z, and normally it is H2 to the power of 3 by 2 minus H1 to the power of 3 by 2, and H is up to exactly center, we are up to only free discharging, and H1 is top edge. Normally H should be bottom edge and H1 is top edge. Suppose if you see the figure, and this is H1 and this is H here, so H power 3 by 2 minus H1 power 3 by 2, so H power 3 by 2 minus H1 power 3 by 2 plus now you take fully submerged R5s here. This is fully submerged R5s here. The bottom edge is H2 and it is up to H here. So now the equation for fully submerged, so this is CDB. Actually supposed to be H2 minus H1, but in place of H1, this is exactly up to the center, so H2 minus H, and this H is again the water level difference between two reservoirs. So this is H2 minus H and 2ZH. So H is again water level difference between two here. So this is H2 minus H into square root 2ZH. That is flow through partially submerged R5s. Now take a problem on that. So find the discharge through a rectangular R5s. With this R5s part is completed, we go to notches after these problems, mostly after a 5 minutes break. So they find the discharge through a rectangular R5s 3 meters wide and 2 meters deep. So it is a rectangular R5s. He has given width is 3 meters and depth is 2 meters. The water level in the tank is 4 meters above the top edge of the R5s, that is H1. Take C is equal to 0.6. So if you take rectangle R5, so this is R5, he has given the width here and he has given H2 and he has given width, he has given depth of the R5 here, D here. So then H1 is equal to H2 minus D. For example, if he is given H1 and let us say H1 or H2 given and D is given, then find out the other value. Let us say H2, he has given H1 and he has asked to find out H2 and D is given. So H1 plus D is equal to H2 and B the width here. That's what the problem means. So he has given the rectangle R5 is width B. So the equation is 2/3 CDB root 2Z H2 3 by 2 minus H1 3 by 2. H2 power of 3 by 2 minus H1 to the power of 3 by 2. So the width is here. The width is B, which is equal to 3 meters wide, is here. and depth is given, and above the top edge means H1. So he has given H1 and the depth D, H1 and the depth D. So H1 is 4 meters and H2 is equal to H1 plus depth, H1 plus depth. So this is H to the power of 3 by 2 minus H1 to the power of 3 by 2. So then what is H2 here? H2 is equal to 4 plus 2, 6 here, and this is 4. So 2/3 CD, coefficient of discharge is 0.6 and B is 3 meters here and G is 9.81 and H to the power of 3 by 2 minus 4 to the power of 3 by 2, you can straight away get actual discharge in meter cube per second. And the second problem. Find the discharge through a full serpent orifice of width 2 meters. If the difference of water levels on both sides of the orifice is 80 centimeters. The height of water from top and bottom of the orifice over 2.5 and 3 meters respectively, take CD is equal to 0.6. So this is the problem of fully serpent orifice of width 2 meters, and the coefficient of discharge has given. So the coefficient of discharge is 0.6 and width is 3 meters here, and he has given from the top and bottom of the orifice H1 and H2 has given. So H1 is 2.5 meters and H2 is 3 meters here. H2 is 3 meters and H1 is 2.5 meters, and the water level difference on both sides of the orifice is 80. Suppose if you see the fully discharged orifice, so he has given the value of H1 and H2, the head with reference to top edge and bottom edge of the orifice, H1 and H2, and this H is the water level difference between two reservoirs. So he has given H1 and H2 and H. So I can get the solution. So Q actual discharge is CD is 0.6 and B is width is 2 meters here and H2 is 3 meters and H1 is 2.5 and square root 2GH, where H is the water level difference between two surfaces here, that is 80. So you need to take not 80 directly, it is required to take 0.8 meters, 0.8 meters, need to take 0.8. Then notches. So rectangle notch, once again we have different types of notches are there. And before we go into this, once again go back to the discussion of orifice and mouthpiece. The quotient of discharge of orifice varies from 0.6 to 0.7. And quotient of discharge for the mouthpiece, because we are having problems on mouthpiece also. More or less same equation. Mouthpiece means we'll be connecting a length, small length of the pipe, which is equal to 2 to 3 times diameter, of orifice. Because of that, the losses are less for the mouthpiece and the losses are more for orifice. And the quotient of discharge for the mouthpiece is 0.855, somewhere around 0.85. So quotient of discharge for the mouthpiece is 0.85 and quotient of discharge for the orifice is 0.6 to 0.7. For small orifice, a circular orifice, the quotient of discharge for small rectangular orifice Q is equal to CD into A multiplied by square root 2GH. Similarly, for mouthpiece also, it is CDA into square root 2GH. So where A is the area of cross section of orifice or mouthpiece, and H is the head above center of orifice or mouthpiece. More or less, orifice or mouthpiece, the equations are same. Don't confuse while you are doing the problem. Only difference is the quotient of discharge is same. The equation is same. The quotient of discharge is different. Quotient of discharge for the mouthpiece is 0.85 and for the orifice is 0.6 to 0.7. The equation is same. So A represents the cross section area of orifice and A represents the cross section area of mouthpiece. That is the only difference. Now the other chapter is the notches. We'll complete notches also today. We will take because this is the another chapter in this one. We'll take a short break and we'll be back. So again, refresh, take a 5 minutes gap, and take water, and again come back in 5 minutes. Be back. Okay, come back to our discussion. So I have completed R5s. Moth is also exactly the similar lines. And now it is notches here, notch, which is of practical significance. For example, take a sketch here, notch. Earlier, we obtained discharges for pipes with the help of intermediate orifice meter and velocity with the help of pitot tube, and orifice and mouthpiece for measuring the discharge in a small tank. Now we can use notches for finding out the discharge through channels, a channel. And this is a notch here. Notch is a opening provided in the side of the tank, a small channel. So take a small channel and the opening is provided in the side of the channel. So for finding out what exactly the quantity of water which is flowing in the small channel. The application of practical relevance, and you might have seen trapezoidal notches also for measuring the rate of flow, actual feeds, what exactly the quantity of water which is flowing through a small channel with the help of a trapezoid notch. It's a natural occurring shape. So the practical application of notch is for finding out the discharge which is flowing through a small channel. Discharge which is flowing through a small channel. So here you have a different terminology. One is called NAPPE, N-A-P-P-E. Suppose if you see here, this is NAPPE. It is also called VN, V-E-I-N. NAPPE or VN, both are same. NAPPE is the sheet of water which is flowing through a channel. So this is a sheet of water here. This is a sheet of water here. Sheet of water here which is flowing through a small channel. And this is called crust or sill. Important objective type. What is a crust or sill? So crust or sill is the bottom edge of the opening over which water flows. Crust or sill is the bottom edge of the opening over which water flows. So this is the bottom edge here. Bottom edge here over which the water is flowing is crust or sill. Suppose if you see here up to here the water is suppose if here the water there is no flow, and whatever the flow which is above that is bottom edge here. So bottom edge of the opening is the crust which is the bottom edge or crust or sill, bottom edge of the opening here. Then sometimes he may ask you what is crust height. Crust height. So the crust height here. So from the bottom edge of the opening, so this is the channel bottom. From the bottom edge to the top here, to the top is called crust height. So see here, this is exactly at the bottom, and the vertical distance between the bottom of the channel to the top edge, the crust here. So this is called crust height. So height of the crust from bottom to this level is crust height. All are very, very important. So what is Napier vein or crust? It is also called sill, crust or sill. And crust height is height and Napier vein is sheet of water, important object type. So then we have different types here. Rectangular, triangular, trapezoidal, and stepper here. We have different types here. Rectangular, normally for normal discharge, triangle for low discharges, and trapezoid is actual shape. For example, see the rectangular here. This is the rectangular notch or weir. So weir, once again, like orifice and mouthpiece, notch and weir. Notch is through a small opening.
promotion Day-11 all lectures Prasad
So this is a rectangular notch here and also wear. So difference between wear and notch is also important. So when the flow is allowed through a small మీరు కలవడం మీ క్లాస్కి వచ్చి మాట్లాడతారు 12:30 వస్తాం మీరు కలవాలి ఓకే మేడం కన్వీనియంట్ అడగదు ఎందుకంటే ఆవిడ హెల్ప్ చేస్తున్నప్పుడు మేడంకి అయితే అట్లీస్ట్ మీరు డేట్ ఇవ్వండి మీకు పంపిస్తాను చెప్పేసి సో దిస్ is sorry for a small interruption and we have different shapes here rectangular way and also so the notch is a small place wherein we can utilize the space for measurement whereas the wear is a flow of water to flow over entire length the flow when there is a flow it is called rectangular wear. See here, this is for the entire length. That is the only difference between notch and wear. The equations are same. And this is the triangular shape of notch. Exactly right angle triangle here. This is a trapezoid notch which is actually existing in nature. Trapezoid notch which is existing in nature. This is a step notch. Another type. So these are the 4 types of notches. And we have a another type of L means what is L here? L is the length of the sill of the notch. Length of the sill of the notch. When the length of the sill of the notch, when it is notch without end contraction. When these are not equal, when L is equal to B, we can say this is notch without end contraction. When L is not equal to B, we can say that it is notch with end contraction. Some corrections are there for end contraction. When L is equal to B, L is the length of sill of the notch, B is a bit. When these two are equal, we can say that it is notch without end contraction. When L is not equal to B, we can say that notch without end contraction. So that is also important for objective type. So then we'll come one by one. So this is the classification here: rectangle, triangle, trapezoid, step, and notch with and without end contraction. Now, how you are going to find out the discharge for the rectangle, notch, or wear? Very simple here. Once again, take the section here and L is the length. And what is H here? H is the head available above the crest of the sill of the notch. Crest or sill of the notch. H is above the crest. H is the head available above the crest. This is very, very important. And now the shape is rectangle. How we are going to find out the discharge? So it is required to find out the quantity of water which is flowing through a small channel. Or a notch is connected. And it is the cross section here. This is a rectangular notch here. The length is L here. Again, take a small strip for which the velocity is uniform. Take a small strip. The velocity is uniform. So for the small strip, the area, so the DH is thickness and length is L. So the area of the small strip is L into DH. Then what is the velocity of water which is flowing through a small stream? So square root 2g h. H is small h, not capital H here. So the velocity of water which is flowing, velocity of the water which is flowing through the notch is square root 2g h, where h is its location with reference to top. So now we have the area. So L into dh and the velocity is square root 2g h. So L into dh into square root 2g h is the theoretical velocity. Theoretical discharge. Area into velocity is theoretical discharge. And actual discharge is equal to CD multiplied by theoretical discharge. So the actual discharge which is flowing dq, which is flowing through a small stream, is equal to CD L into dh. CD L into dh into square root 2gh. This is a small value. This is small h. So CD is quotient of discharge and L into dh is the area and square root 2gh here 1 by 2. And for finding out the entire area, so integral dq and CD is constant, L is constant, and 2g also can take outside. So CDL root 2g, this is a constant here, and integral h power 1 by 2 into dh. So h power 1 by 2 into dh is 3 by 2, h power 3 by 2 by 3 by 2, by 3 by 2 it is there here 2 by 3. So now q is equal to 2 by 3, 2 by 3 CDL square root 2g h power 3 by 2 written right. Remember this equation very important for 2/3 CDL square root 2g h power 3 by 2. Similarly for triangle notch or VA, rectangle notch or VA, triangle notch or VA. So discharge over a triangle notch or VA. The triangle notch. So take the triangle notch here and the same procedure. Take a small strip. Take a small strip. The thickness of the strip is dh here, and h is its location. H is the location on the top here. So now we have velocity is known, square root 2gh velocity is known, and quotient of discharge can be obtained. And then how will you find out the area? So why I am stressing this here is students are doing mistakes while arriving. Some of the students are doing mistakes while arriving in small area. So this is dh here, thickness is known here, and find out the width here, AB. AB is required. So the triangle notch total area is, total angle is theta. Triangle notch total angle is theta. So take half here, AC go. And angle is half of the angle is theta by 2. It is symmetry. Half of the angle is theta by 2. And this is total one is h here. Total is h here and h. And it is required to find out AC. So AB is equal to AC plus CB. It is required to find out AC. So then AC is equal to take tan theta by 2. Tan theta by 2 is equal to AC by h minus h, opposite by adjacent side. So tan theta by 2 is equal to AC by h minus h, and AC is equal to h minus h tan theta by 2. And then we have the value of AC, which is equal to h minus h tan theta by 2. And what is CB? And AC and CB are equal. AC and CB are equal. They have taken theta by 2 and here also theta by 2. And then AB is equal to 2 times AC. Then 2 into h minus h and tan theta by 2. AB is equal to 2 into h minus h tan theta by 2, and thickness is delta dh. And square root 2gh is the velocity. Now you have everything here. The area is known and velocity is known. And the equation is dq dq is equal to CD, quotient of discharge, and h minus h, this is theta, tan theta by 2, h minus h, tan theta by 2, and dh, and square root 2gh. Square root 2gh, the small h here. So dq is equal to CD, 2 into h minus h, tan theta by 2, dh into square root 2gh, and find out for the entire strip. Do integration. So 8 by 15, CD root 2g is a constant value, and tan theta by 2, h bar 5 by 2, tan theta by 2 is also constant. And you can do integration here. So the resulting equation is 8 by 15, CD root 2z, tan theta by 2, h bar 5 by 2. Try to remember this triangle notch equation also, instead of doing derivation, just I have given steps, so that you can reproduce if it is required for the gate examination. Briefly, I am also introducing the steps here. And now this charge is 8 by 15, CD root 2g, tan theta by 2, h bar 5 by 2. The other one is discharge over a trapezoidal notch. Then how will you do for trapezoidal notch? So this is also simple here. So you can take this is ABCD. ABCD is a rectangle. ABCD is a rectangle, and BCE and ABF. If you see here, so take two aspects here. One is it is a combination of trapezoid, means it is a combination of trapezoid notch or here. So it is a combination of both rectangle and triangle. So this is a rectangle notch, ABCD is a rectangle notch here. This is H here, LH, and take ADF and also combined BEC is a full triangle. So the triangle, you can take this right angle triangle is ADF, and again take right angle triangle BEC, and theta by 2, and the total is a triangle notch. So the trapezoid notch is a combination of rectangle notch and triangle notch. So rectangle is ABCD, and the triangle is the sum of FAD plus BEC, and the total angle theta. So you can take both rectangle and triangle notch, and triangle trapezoid notch, the discharge through trapezoid notch, which is equal to sum of discharge through rectangle notch and discharge through triangle notch, same equation. Discharge trapezoid notch, which is 2/3 CDL. So L is length of the cylinder of the notch. So this is L here, length of the cylinder of the notch, and H is head available here, head above cylinder of the notch, and theta is the angle here. So 2/3 CDL root 2g into h bar 3 by 2. So this is for rectangle notch, and this is for the triangle notch, 8 by 15 CD root 2g tan theta by 2, h bar 5 by 2. So it's a combination of rectangle and triangle. It's a combination of rectangle and triangle. Now take problems on that. Problem. So determine the height of a rectangle weir of length 5 meters. Determine the height of a rectangle weir of length 5 meters to be built across a rectangle channel. The maximum depth of water on the upstream side of the weir is 1.5 meters, and discharge is 1.5 meter cube per second. He has given height of the rectangular weir. Of length 5 meters to be built across a rectangular channel. So the maximum depth of water. So this is simple here. Length he has given 5 meters on a rectangular channel. The maximum depth of water. So upstream side, the maximum depth is 1.5. And he has also given discharge 1.5 meter cube per second. So we have the equation here for a rectangular channel. So 2/3 CDL square root 2G H bar 3 by 2. So you can assume CD is equal to 0.6. PD is equal to 0.6, you can assume. And you can use this equation here, Q is equal to 2/3. CD is 0.6 and L is 5 meters, L is 5 meters here and square root 2Z and H is not known. Discharge you can take 1.5 meter cube per second. So discharge you can take 1.5 meter cube per second, 2/3, CD is 0.6, L is 5 meters, square root 2G, G is 9.81, you can find out H. That H is equal to 0.309 meters here. Now we have also to find out rectangular weir of length. So total head available on the upstream side is 1.5 meters and head above sill is 0.309. The difference is the height of rectangular weir. So most of the students they are giving the value of H as the height of rectangular weir, but which is not correct. So you will be getting only the head above the sill of the notch. For finding out the height, cast height. So the total head available on the upstream side, total is he has given 1.5 meters. So this is discharge and this is total height on the upstream side 1.5 and 1.5 minus the head above the sill is 0.309. So which is equal to 1.191 meters. Second problem, find the discharge over a triangular notch of angle 60 degrees when the head over the triangle notch is 0.2 meters. It has given each and every value. Asked me to find out discharge. So CD is equal to 0.6 here. CD is 0.6 here. And square root 2G, G is 9.81 and theta is 60 here. Tan 60 by 2, tan 30. And head over the triangle notch, he has also given head here, straight away 0.2 meters and asking you to find out the discharge. The equation is, you should remember the equation here, otherwise you may not be able to do the problem. Try to remember these equations. For all the equations, rectangular notch, triangular notch, if you remember rectangle and triangle, so you can automatically get trapezoid and step notch. Similarly, small R5s, large R5s, rectangular R5s, fully submerged R5s. If you remember fully submerged rectangular notch, you can also get partial submerged R5s. Similarly, remembering the equations is very much essential, and without that we cannot able to do the questions answers in the GATE examination. So 8 by 15, the value of CD is known here 0.6 and square root 2Z and theta is 60 and H is 0.2 meters. You can slightly find out discharge, which is meter cube per second. Then the other one, discharge over stepper notch, discharge over stepper notch. Yes. So this is the stepper notch here. So if you see the shapes here for the stepper notch, so this is a rectangle here. This is one rectangle here. So you can divide this into 3 rectangles here. Divide this into 3 rectangles here. So the first rectangle here is L1. And what is the head here for first rectangle? So it has given H1 here and H2 here. And if you take the difference H1 and H2, and here the limits are H1 and H2. And take second rectangle, and for which the length is L2, and this is the H3 here. The head here, bottom is H1, and second one is H2, and third is H3. So the second one is the length is L2, and heads here, the limits here is H2 to the H3. And the third, again another rectangle, combination step notch is a combination of rectangle notches. Step notch is a combination of rectangle notches. 1, 2, 3. So for the third rectangle notch, again the length of sill notch is L3, and this is H3. So then use the equation here, we can the first rectangle notch with L1 and limits H1, H2, and second rectangle notch L2 with the limits H2 and H3, and third rectangle notch with H3. The equation. So this is our step notch. The first one, 2/3 CD L1 square root 2Z, and because the limits are H1 and H2, H1 to the power of 3/2 minus H2 to the power of 3/2. The sum of the students, they are taking 2/3 CD L1, 2G, and square root 2G H1 they are taking. They are taking straight away this equation, and they are taking H1, H2 and H3, but not correct. The limits are different. So here the limits are H1 here and H2 here, and here the limits are H2 and H3. You need to take that. So 2/3 CD L1 square root 2Z and H1 to the power of 3/2 minus H2 to the power of 3/2, that is for rectangle, first rectangle. And second rectangle, 2/3 CD L2 square root 2Z, H to the power of 3/2 minus H3 to the power of 3/2. And third one is 2/3 CD L3 2G square root 2Z H3 power of 3/2. So this is the dischargeable step notch. If you remember the rectangle notch, rectangle notch or rectangle weir or triangle notch or triangle weir, so you can able to solve any problem of notches, whether the shape is rectangle, triangle, or trapezoidal or step notch. Now ask me the questions. So the first question, match list 1 and list 2 and select the correct answer using the codes given below the list. So RFIs just now I discussed. RFIs for finding out flow rate. So if you see here, RFIs for the flow rate. So the answer C, D is 1. D is 1 for here and here. So the answer should be between C and D. C and D. Okay, then take petard tube or piezometric or condensed. Piezometric or condensed. So piezometric is for finding out static pressure. Piezometric is for finding out static pressure. So then B is equal to 3. So B is equal to 3 and piezometer, B is equal to 3. So then B is equal to 3 here, B is equal to 4 here. And we have the other answer, petard tube C, C4 here. Okay. So then take anemometer here, anemometer A, velocity, piezometer E is for finding out static pressure, and pitot tube for difference between static and stagnation pressure, and R phase flow rate. So the answer is C here. Animator may be slightly confused with animator because all the three you can get, and animator can automatically is the next one. Velocity. Animator for finding out. Animator is instrument for measuring wind force and velocity. Then second question. So given H is height of liquid and B is width of notch, A is cross section area, and A1 is area at inlet, and A2 area at the throat, and CD is the quotient of discharge, not drag here, this is discharge, quotient of discharge. And match list 1 and list 2 and select the correct answer using the codes given below. Discharge through venturimeter. So discharge through venturimeter is CD A1 A2 by square root of A1 square minus A2 square into square root. This is discharge through venturimeter. And B, discharge through an external mouthpiece. So the external mouthpiece, I have told you that the CD is 0.855. So CD is 0.85 into A in square root of H. It might be sometimes the students may not study mouthpiece, but R phase and mouthpiece are same except CD. CD is R phase maybe around 0.6 to 0.7, for mouthpiece around 0.85. So discharge through an external mouthpiece is 0.855 into A into square root of H, that is correct. And C, discharge of rectangular notch. So discharge of rectangular notch is 2/3 CD, B root 2G H power 3/2. This is 3 only, not 5. So 2/3 CD, B root 2G H power of 3/2. 3/2 is correct, not 5 here. This is 3. Might be some mistake by the examiner. So here, the last one, discharge over a right angle notch is 8/15 CD root 2G tan theta by 2. So he has not taken tan theta by 2, which was 5/2. But it is closely resemblance. So this equation closely resemblance, even though there are some small mistakes, but we need to give the answer here. So the answer is A. Some small mistakes are there, maybe topographical, but I have straight away taken from examination IES without changing anything. So, but as it is very close to that, you can take, you can match here, and you can give the answer is B here. Third one. In a submerged R phase flow, the discharge is proportional to which one of the following parameters in a R phase? So instead of that, suppose if you take here any R phase, the velocity, discharge is proportional to velocity, and the velocity is proportional to square root, it is square root 2G H, proportional to H by 1/2, and that head is the difference. This is the square root of, they has given square root also, square root of difference between upstream and downstream heads. So whatever the difference between upstream and downstream, so that you can take for submerged R phase. So if you remember the sketch here earlier, submerged R phase, yes, submerged R phase, fully submerged R phase. So this is between the water level difference between this one and this one. So that is capital H. You know the equation, submerged R phase, this is square root H. This H is the water level difference between the two reservoirs. So this is the question, this was the question he has asked. Four. A fluid, this is another interesting question. A fluid jet is discharging from a 100 mm nozzle and the vena contact formally has a diameter of 90 mm. If the quotient of velocity is 0.95, he has given the quotient of velocity and asked to find out quotient of discharge. So quotient, the relation between quotient of discharge and quotient of velocity, CD is equal to CC into CV. This should be V. CD is equal to CC into CV. So he has given the value of CV, which is 0.95. He has given the value of CV. This is CV, 0.95. Then it is required to find out the correct CC value. CC is the quotient of contraction. Quotient of contraction. You need to give the value CC is a quotient of contraction. So which is equal to the area vena contact formation. I have discussed with you. Vena contact formation has a diameter of 90 mm. So the area at the vena contracta by actual area here. So the quotient, this is area at the vena contracta which is equal to pi by 4 90 square by the actual area pi by 4 100 square. So because both are in mm and mm, and you can set away huge here and the ratio is 0.81. So now the ratio CC is 0.81 and CV is 0.95. So CD is equal to CC into CV. So 0.81 and 0.95, 0.7695. And this is the answer, 0.7695. Interesting question, very, very important. The other questions here. Which of the following or related to measure the discharge by rectangular notch? Obviously, rectangular notch is 2/3 CD B root 2G H power 3 by 2. Answer is C. 2 alone, not 1 and 3, 2 and 3, etc. This should be H power 3 by 2. So this is correct. 2/3 CD B root 2G H power 3 by 2. The answer is C. Match list a measuring instrument with which two valuable to be measured. More or less this type we have discussed earlier also. Hot wire anemometer, which is for velocity fluctuations, and petard tube for stagnation pressure. The stagnation pressure, as you know, it is sum of static head and dynamic head. Stagnation pressure is also called total pressure. Sometimes we may be giving total pressure and sometimes we may be giving stagnation pressure. Stagnation means both static and dynamic. So petard tube gives stagnation pressure. And V notch, VR, notch or VR, whatever it is. So it is for the discharge. And tachometer for speed. So the answer is D. So 90 degrees V notch, a standard 90 degrees V notch is used to measure discharge. The discharge is Q1 for height H1 above the sill and Q2 is the discharge for height H2. Then he has asked to find out if H2 by H1 is 4, then Q2 by Q1. Then straight away, the equation is 8 by 15 root 2g tan theta by 2 V notch. 8 by 15 root 2g tan theta by 2 H bar 5 by 2. And Q is proportional to H bar 5 by 2 and all the other values are constant, let us say, not necessary. And Q1 is proportional to H bar 5 by 2 and Q2 by Q1 is equal to H2 by H1 to the power of 5 by 2. So then H2 by H1, so this is not H by H2, this is H2 by H1. So H by H1 is 4 here, 4 to the power of 5 by 2 and the answer is 32. So the answer is A. A. This is another interesting question. A triangle notch is a more accurate measuring device than the rectangle notch for measuring Which one of the following? A triangular notch is more accurate measuring device than the rectangular notch. For measuring which one of the following? So the triangular notch is always for low flow rates. When the discharge is low, so because the shape is, when the discharge is low, you can get the actual value. That means, as you know, the notch is for measuring the discharge, which is flowing through a channel. So you can use a triangular notch for measuring low discharges, low flow rates. So the answer is A. So this is about notches and archives. The questions were given in the GATE examination I have taken, and you can easily score marks in this chapter. Because some time is there, I will take some objective questions now. Some 20 to 30 questions now. General questions. Objective questions set 1. So I'll try to give this one. So here some of the questions. Set 1. And also tomorrow also I will take lift and drag chapter, and I will try to take some more objective questions also in the next class tomorrow, maybe perhaps in the last class. Some of the questions here in this chapter. The water flowing in a pumping or the flow in a pipe or channel said to be uniform. So you need to know what is exactly meant by uniform flow. So uniform flow means uniform is always between velocity and distance. So go back to the fundamentals of steady flow and uniform flow. So steady flow means any property with reference to time. This is the uniform flow. This is the uniform flow. Uniform flow means the velocity with reference to distance. The liquid particles at all sections have the same velocity. So that is, the answer is A. When the liquid particles are having the same velocity at all sections at a particular time, that is called uniform flow. And second question, the answer is A. For one, answer is A. Second question, the loss of head at the entrance in a pipe. The loss of head at the entrance in a pipe is entrance loss is 0.5 V square by 2G. So the answer is B. The other question, critical velocity. What exactly mean by critical velocity? So critical velocity, the velocity at which the flow changes from laminar to turbulent. So during my discussion, I told you critical velocity is the velocity at which the flow changes from laminar to turbulent. So the Reynolds number is less than 2000 is laminar flow, and more than 4000 is turbulent flow. So here, this is the critical velocity. The answer for 3 is C, critical velocity. 4. So critical velocity you need to number Reynolds number also. So between, when the Reynolds number is between 2000 to 4000, you can get that flow velocity is critical velocity. A steady uniform flow is true. When the pipe is long and flowing at a constant rate, you can get a steady uniform flow. Steady means all the properties are constant with reference to time. Uniform means the velocity with reference to distance is constant. Steady uniform flow. The example is a long pipe at constant rate. A non-uniform steady, flow is steady. So when the flow is steady, the rate is constant. When it is non-uniform, that means the diameter is not same, an expanding tube. A non-uniform steady flow means it is expanding tube at constant rate 5B. 6. A flow through expanding tube at increasing rate, and the cross-section area is not constant and the rate is not constant, then it is unsteady non-uniform flow. It will confuse you particularly between steady, uniform, unsteady, non-uniform, steady, non-uniform, or something like that. The combinations also should have a better exposure towards that. A flow through an expanding tube at increasing rate is A, 6A, unsteady, non-uniform flow. The hydraulic jump is an example for unsteady and non-uniform flow. This is example. And a flow through a ventrimeter, because the cross-section area is not uniform, the flow rate is same. So steady non-uniform flow. Steady non-uniform flow. Ninth question. The flow in gradual GVF is gradually and rapid varied flow, or one is gradually varied is steady non-uniform, and rapidly varied is unsteady non-uniform. The other one, Bennett's equation. This is a combination of all objective questions from all the chapters. You should have a confidence in answering these questions. So Bennett's equation is applicable between any 2 points. Is definition, fundamental definition, steady irrotational flow of an incompressible fluid is a Bennett's equation. D. Answer for 10 is D. 11. The difference between a total headline or total energy line and hydraulic gradient line. So as you know, hydraulic gradient line is a physiometric line. P by W plus Z. P by W plus Z is hydraulic gradient line, and total headline is P by W plus Z plus V square by 2Z. So difference between is only velocity head, V square by 2Z. You have discussed when you have discussed this when we have studied the pipe flow, when you have discussed pipe flow. The lower limit of critical Reynolds number in pipe flow value approximately equal to 2000. Lower limit is 2000, 2000, 4000 critical lower Reynolds number and upper Reynolds number between laminar and turbulent flow. The answer 12 is A, 2014. For rough pipes, the friction factor depends on, it is a rough pipe, definitely roughness parameter, and also depends on Reynolds number. So the 14, the answer is D. So the head loss 16. The head loss in turbulent flow in pipe varies. So B varies approximately at the square of the velocity. So HF is equal to FLV square by 2ZD. So this is square of the velocity, as head loss depends on the square of the velocity. So answer for 16 B. Pressure drop per unit length number 17. The pressure drop per unit length in laminar flow between closely spaced parallel plates. Huygens equation 32 G.V.R by gamma d square. The only thing which is close to this. We have a small mistakes in giving the examples, but very close to that answer we can give. So B, but should not give no answer for that. So 32 G.V.R by d square is the pressure drop. P1 minus P2 is 32 G.V.R by d square. So this might be new. 17B, 18. The velocity distribution in a turbulent flow follows. This is a logarithmic law. 19A, 20. The shear stress in laminar flow between two parallel plates. Yesterday also we have discussed this. 0 at the midplane and linear with the distance from the midplane and maximum at the boundaries. The shear stress in a laminar flow 0 at the center and varies linearly and have a maximum at the boundaries. So this is answer for 20 is C. The 21 is siphon. The maximum negative pressure occurs. Siphon. The maximum negative pressure occurs at summit. So the low pressure you can expect only at the top, that is summit. Summit is the highest portion of the siphon. We have inlet line. We have given inlet. So inlet means this is between one reservoir to the summit, left side reservoir to the summit. Outlet is from the summit to the outlet. And the answer is summit, 21A. In an inclined pipe, the pressure difference at the two ends is U2. So the pressure difference means the losses. So whatever it is, because it is due to difference of elevation. In inclined pipe, the pressure difference due to difference of elevation here. So 22D. So then 23. The loss of head due to sudden expansion when velocity changes from 5 to 4. Loss of head due to sudden expansion, the equation is, as you know, V1 minus V2 whole square by 2Z. So you should remember the equation appropriately. Within no time, you should be able to reproduce that. So the equation is V1 minus V2 whole square by 2Z. So it has given V1 here, V1 is 5 and V2 is 4. So 5 minus 4 whole square by 2 into Z, 2 into 9.81. So the answer is 0.05. So the equation is V1 minus V2 whole square by 2Z. So V1 minus V2, 5 minus 4 is 1 by 2 into Z, 1 by 2 into Z, 2 into 9.81. So this is 0.05. So 23A and 24. So these two are parallel pipes here, and this is D is the capital D and the small d is here. What is the relation between D, small d and N? So this also we have done when we consider the analysis of pipeline. So the equation is D is equal to D by N, where N is the number of pipes. So D is equal to D by N with power of 2 by 4. So the 24, the answer is D. In a siphon, the hydraulic gradient line lies. Normally, it is above center line, but here the siphon, sometimes it is negative pressure and some portion is different. So partly above and partly below the center line. That is answer 25D and 26. When the pressure drop in a 60 centimeter diameter pipeline is 700, pressure drop in a 60 centimeter diameter pipeline is 700. The length of the pipe is doubled. The pipeline length is earlier 60, now it is doubled to 120. What is the new pressure loss will be? So as you know, the equation for pressure drop P1 minus P2 is 32 BVL by D square. He has given diameters here. So it is proportional to values here. So the answer here is, that is a double here, this is also double. So it is 1400. The discharge of the pipe is doubled. So what should be the loss of head? The loss of head is FLV square 2ZD, FLV square by 2ZD, and B, if we convert into discharge, so V square means Q square, and if it is double means Q square, 2 square is 4, so that means increases 4 times. So discharge is proportional to, or head loss is proportional to V square. HF is equal to FLV square by 2ZD. HF is equal to FLV square 2ZD. So HF is proportional to Q square and Q is doubled. So that means 2 times H, 2 square is 4. So increase 4 times. So 28, the answer is B. 29, the ratio of inertia and viscous force is obviously Reynolds number. Inertia force, viscous force, acting in any flow, ignoring other forces, is Reynolds number. And ratio of inertia to gravitational force is Froude's number. So the 29 answer is C, 30 answer is B. 32. A 10 centimeters diameter, 500 long, 500 meters long, length given and diameter given, equivalent to diameter given dash length here. So equivalency, we have the value L by D5 is equal to L by D5, L1 by D1 5 is equal to L2 by D2 5. So use that equation, L1 by D1 5 is equal to L2 by D2 5. So the answer is 16,000. 32 answer D. If the coefficient of friction is 0.008, what is the Reynolds number? So F is equal to, as you know, F is equal to 64 by Rn. F is equal to 64 by Rn, but this is the value is equal to 4F. So normally this is into 4, so 0.032. So normally the coefficient of friction varies from 0.02 to 0.03. 0.008 means it is very low value, and this is a small f here which is in 4F. 4F means if you consider 4F is equal to 64 by Rn, 4F is equal to 64 by Rn, then the answer is 2000. So if you consider F is equal to 64 by Rn, the answer is 8000. So because the value as it is very less and so this should be 4F, and but one should get marks whether it is given A or B or safe B. So because I can take F is equal to 65 by Rn or 4F is equal to 65 by Rn, and so that we can find out Rn. So he has given coefficient of friction is 0.24 and changes constant is. So relation between changes constant and coefficient of friction, C is equal to square root of 8G by F. C is equal to square root of 8G by F. So 8 into G is 8 into 9.81 by 0.24 square root. So that is 55, 36, answer is 55. 37. The equivalent pipe which two parameters are the same. So equivalent pipe, the head loss due to friction and discharge should be same. The answer is C. 38. For flow through which of the following is normal turbulent? So municipal water lines is turbulent. So 38 answer is C. 41. The slope of hydraulic gradient incline. So a slope is HF by L, and it is HF is FLV square 2ZD, and V is if you convert V in Q and D square, so this is proportional 1 by D5. 41 answer is D. 42. The most accurate expression for velocity flow through a siphon, so V is equal to, the answer is C, square root of 2GH by 1.5 plus 6L by D. 42, the answer is C. Last question for today. In a laminar flow of kerosene, the discharge varies from 600 to 1200, the corresponding head loss. So HF is equal to FLV square 2GD or FLQ square. So HF is proportional to Q square, and HF1 by HF is equal to Q1 by Q2. So he has given by 600 by 1200. 600 by 1200 is, you can take square, so 1 by 2 square, 4. 4 into 2, he has given 2. 8. The answer is 8 here. So you can take HF1 by HF2 is equal to Q1 by Q2 whole square. So that the 43 answer is B. 44. In a laminar flow, the diameter varies from 600 to 300 meters. The corresponding head loss varies from. So HF is proportional to 1 by D5, FLV square by 2ZD, and velocity is you can take Q square by area square. So this will be 1 by D5. So HF is proportional to 1 by D5. So HF1 by HF2 is equal to D2 by D1 to the power of 5. So you take 300 by 600 here to the power of 5 into 5. So this is 160 meters. So 44, the answer is B. So thank you very much for our nice hearing, and also thank the organizers for spending their time in for the noble cause. And tomorrow we will meet again at the 10:30. That is the last class, and